Hi, good afternoon everyone. I am Nishchal Gruvachari presenting data-driven modeling of power electronic converter with grid support functions. And currently I am PhD student at South Dakota State University. Let's talk about motivation and objective of this poster. With the increase in inverter-based generation integration in the modern grid and their different dynamics compared to the traditional generation, power system dynamics need to be assessed using accurate models. This becomes of particular importance when they also provide voltage and frequency support to the grid. In the past, these dynamics were largely neglected as the percentage of converter-based generation was relatively low and the converter had a passive role as they were not actively contributing to voltage and frequency control of power systems. Neglecting the impact of power electronic converter was possible as power system dynamics are largely dominated by large synchronous generators with well-defined models. But as the future energy demand is made by converter-based generation, models that accurately represent the interaction between the grid and the converters are essential because we are unknown of controls and converter design. The main objective of this poster is to present the data-driven modeling of power electronic converter with grid support function to study the power system dynamics. A simulation setup of grid-connected inverter system operating in current control mode is shown in Figure A. The inverter is connected to the electric grid through a low-pass filter with inductance LF. The inverter is being operated in the grid following mode, injecting the reference active and reactive power commands P** and Q** respectively, which is obtained either only from the normal function of inverter or from both having normal function along with grid support function features as shown in Figure B. A phase lock loop is used to track the phase angle of the grid. Then a current controller is employed to control the current being injected into the grid. For the presentation purpose, only the volt-var mode is discussed. The droop curve of volt-var mode is shown in the figure. Here, the volt-var mode is divided into 6 linear regions and 6 linear models are developed to represent the volt-var mode. The flowchart of system identification for data-driven modeling is shown in the figure. To determine the transfer function of the grid-connected inverter, the dynamic response of the inverter current is observed when there are step change in the grid voltage. Based on the collected input-output data, a set of models with different number of poles and zeros is fitted to the data. System identification toolbox available in MATLAB Simulink is used to obtain the different transfer functions of the grid-connected inverter. The fit of the model is calculated using a metric such as normalized root mean square error and AKK final prediction error. From the base fit, the transfer function of the grid-connected inverter is chosen. The result shown shows the output of inverter current when the voltage is perturbed in the linear model 1. A transfer function with 2 poles and 1 zero seems to provide the base fit. Furthermore, the AKK final prediction error metric is also low. The simulated model against the measured data is shown in the figure. The simulated model is the response that is computed based on the fitted model, using the test data as the input. The fit obtained in this case was 99.68%, which is very accurate. The dotted lines illustrate the 95% confidence interval of the estimates. So, in conclusion, data-driven modeling of power electronic converter with grid support function were presented in this paper to study the power system dynamics. The transfer function of power electronic converter was developed for voltage perturbation using system identification tool from MATLAB. Based on different metrics that measure the goodness of fit, a second-order model was identified to be the base fit. In the future, we intend to explore the frequency dynamics of inverter when there is frequency perturbation. This work is supported by US National Science Foundation, US Department of Energy, and STSU Joint Research Scholarship and Creative Activity Challenge Fund. Thank you.